Hello and welcome. So today I'm going to be going through one of the Comsol tutorials for ultrasound. This one in particular is high intensity focused ultrasound, or HIFU, propagation through a tissue phantom. So to find this tutorial, I went on and looked up ultrasound tutorials Comsol on Google, and I found this one to be pretty relevant because it covers both high intensity focused ultrasound and also tissue phantoms. So from just what I skimmed, it seems like it'll be a good way to model the nonlinear effects of transducer and with tissue. Some reasons of why you would want to model high intensity focused ultrasound with tissue is because we're starting to use high intensity ultrasound to treat different diseases, and we're also using it as therapies. Here they list thermal ablation of tumors, which is destroying tumors with the thermal effects or cavitation effects of high intensity focused ultrasound, transcranial surgery, which is kind of broad. I would say that you could say maybe you're using these effects, maybe you're using shear forces. It's a general cover, and also says shockwave lithotripsy, which is breaking up kidney stones. So it kind of covers it all. It's not limited to these, but these are just saying here's some applications of this and why maybe we want to model this. So I think in the future this is going to be a very important tutorial, and I'm happy to start with this one. So we have our cover slide here. And the introduction. I already read this before starting, and I'm going to go through and kind of highlight some areas where I was confused. So we were talking about high intensity focused ultrasound is used in many ways for biomedical applications. Okay, we know that. HIFU is focused on a small focal zone. Okay, high intensity focused ultrasound focused, so focused to a small local zone. Let me change this. Green, we kind of know this. So HIFU is focused to a small focal zone where intensities reach higher levels. Okay, so we have intensities from the, can I delete that? Yeah. So we have HIFU, and we have our intensities, the intensity portion, small focal zone, focused, high intensities, right there, and then just ultrasound. So pretty simple, high intensity, focused ultrasound. And we're talking about the nonlinear effects becoming significant. And I kind of have an idea about this, but I'm not 100% certain on it. I'm about 70% there, so I'm highlighting it. I kind of want to come back to this and kind of answer, what do we mean by nonlinear effects? What nonlinear effects are we actually looking for? Propagation of finite amplitude sound waves. Okay, so like we're seeing very small amplitude sound waves. Propagation of very small amplitude sound waves, is that connecting to our intensity? The nonlinear nature of the phenomenon results in energy transfer from lower to higher harmonics. Okay. Lower to higher harmonics. That's raising a question for me, because I know about the harmonics within an ultrasound system bouncing back and forth, but exactly what do we mean by we're transferring energy from lower to higher harmonics? Why is it important that we're going from low to high? And the contribution of higher order harmonics grows with propagation distance. I'm going to change this color here. So the contribution of higher order harmonics grows propagation distance. So the contributions, the effects of these higher order harmonics grows with the propagation distance. So the distance away from our transducer or away from our focal point. Now, I'm assuming that they're saying it's growing away from our transducer element, because in the case of a focusing element, I want to draw with this, maybe this color. Okay. If we have a transducer here and we have a focusing lens on the end of that transducer, that lens may be a concave shape like this, and what happens there is our beam line trajectory is going to be focusing a certain point and then getting bigger, almost like we're using glasses. And this is just where our waves are all having a high, what's the word I'm looking for? Where they're all overlapping. We have a lot of superposition at this point here, giving us our high intensity. So are we saying that the higher order harmonics is growing some distance to this point? Because at some distance, it's not going to keep growing. It's not exponential. It stops at one point, and then it gets worse off after that. And usually the shape that we have, here it crosses at a point, but usually, like in the case with a visual lens or like an optical lens, that's a better way to say it, we have some blurring, and our shape is more like a teardrop, kind of has a tail on it, and this is where maybe 90% of our energy is, and then shape inside of here with 99%. I'm just making up these numbers, but it's just to say that we have an area inside which has most of our energy, area outside less, and then as we go further out, we get less and less energy in, and then maybe less energy is contained in that area. Okay, so now we've gone through the first paragraph. Let's keep going. I'm going to go back to yellow as being what I'm kind of having questions about. This example shows how to model nonlinear propagation of HIFU through a dissipative media. Okay, well, we know what that is. It's a media that is dissipating our waves, which would be our tissue. It says, using the nonlinear pressure acoustics, okay, time explicit physics interface. Nonlinear pressure, acoustics, and time explicit interface. When I see interface, I'm thinking this might be part of Comsol. The interface solves a system of nonlinear acoustic equations in the form of a hyperbolic conservation law. See reference 1. Okay, let's see our references. We'll just do this first. Model wizard, parameters, rectangle 1. Reference 1. Reference, oh, right here. Okay. A conservation numerical scheme for modeling nonlinear acoustic propagations in thermoviscous homogeneous media. Conservation numerical scheme. Okay. We'd have to look at that. Okay, so still having a question then. So we'll still kind of wonder, what is this hyperbolic conversation law? What are we conserving? Using the discontinuous Galerkin finite element method, DGFEM. So I'm familiar with finite element methods, but maybe I need to see which one this is. What exactly is the Galerkin method? The discontinuous method. And an explicit time and integration scheme. Okay. Time integration scheme. So we're integrating time. Okay. So it's just happening over time. Yeah. The used approach is suitable when the cumulative nonlinear effects, that is, those cumulated through propagation, dominate the local nonlinear effects. Okay, so we're saying that here our cumulative nonlinear effects is going to be greater than our local nonlinear effects, greater so much that they dominate that. And if we were using an equation of cumulative nonlinear effects plus local nonlinear effects, this term would become the dominant term, and we'd be looking at that one. Okay. In this model, the emitted signal is a tone burst pulse, okay, that occupies only a limited part of the computational domain on its way. Not really having questions there. Adaptive mesh refinement is used. So I'm thinking adaptive mesh means that the model that we're using is going to have higher geometry in it so that we can have higher resolution. It's adaptive mesh. Whatever mesh we have is going to be getting high resolution or something. Refinement is used for automatic remeshing. Yeah, so we have remeshing. Okay. Following the signal propagation. So maybe the mesh gets messed up as the signal propagates and they have to remesh at a time. So okay, that's cool. It's a little feature of Comsol. This ensures that the mesh is fine enough to resolve the higher order harmonics where it's required. Okay, so that's like what I said. Adaptive mesh means our mesh is going to be holding more resolution. Our mesh will be changing as we run the simulation to have a fine enough mesh. Okay. So that was the introduction. Okay. So now I'm getting, the second time I'm reading this, I'm actually getting a better idea of what we're going to be doing. Okay. Model definition. The focusing of an ultrasonic signal is typically achieved either by using a phase delay or a focusing lens on the transducer side. Okay. The focusing of an ultrasonic signal is typically achieved by either using a phase delay or a focusing lens. I'm very familiar with a focusing lens on the transducer side. But a phase delay, so why would we use a phase delay? I gotta think about this. So how is that gonna help us? We're gonna delay our phase, because we know that to get, erase this one here actually. I can't recall the units here, but talking about a phase delay, I should look at my notes. We have one sine wave, and then we have a cosine wave, and the cosine wave, it's lagging by 90 degrees. Oh, that's okay. Well, it's something like electricity voltage lags something by 90 degrees. So are we trying so we know that voltage lags it. We use a phase delay to reach our resonance frequency. So I want to learn more about that, the phase delay. That sounds interesting. Okay. In this model, a spherically focused ultrasound transducer. Okay, so kind of like what I was showing here. This is a line, but I was thinking that this was a ceramic disc. So when they say what do they say? Spherically focused. So wait, they say spherical though. What I was thinking is something like this with a thickness on it, like a piezoelectric ceramic PZT. But they said spherical. I don't know if they mean circular. They said spherical. With a concave lens, and this is the concave lens that I was talking about. The lens that just looks like that from this side, and if we're maybe doing a 3D shape, and then we have a circle on the bottom here because this is a 3D shape, so this is concave like that. In this model, spherically focused ultrasound transducer with a concave lens is used to emit the signal. The transducer housing and the lens are assumed to be rigid. The model setup is shown in figure 1. The model geometry is axially symmetric. So this is my idea of what it is. We're going to see a thin disc, and we're going to see a concave lens on it. They'll look like this. Model 1. Okay, so if this is model 1, yeah, we're seeing it here. This is the... Let me actually change this a little bit. It's the same thing, only I'm going to add water in front of it. Hold on. So if this was ours, we would have water in front of the... that's the focusing element. So we would have water in front of the focusing element. And then behind it, we'd have this thin disc. And I'll draw the thin disc in... We'll do this color. So this is the thin disc. And I'm just going to say it's an extremely thin disc. And they're mated here. And then there's water here. And then some tissue on the outside. So let's go back here. We have our tissue here. We have our focal zone. Okay. Focal zone coming in like this. And we have we're actually taking the radius from our tissue to the concave part. Oh, I would like to see this circle actually drawn out completely. I don't know if I have a tool here to draw out a circle. That'd be nice. That'd be nice. Because I'd want to see, I don't think it's drawn to scale, but if it was, to see where the actual circle was and where the focal point was. But the focal point is going to be dependent also on our transducer. But yeah, so it's focusing at a certain point. We have a distance from our focal zone to our maybe aperture. I'll get back to that. Okay. So basically, this idea here is probably here. So when they say spherical, they probably just mean round. The spherical lens of radius r and aperture A. Okay, so I was right. So we have... Let's highlight these. We have a spherical lens with a radius r and an aperture A. Emits a signal that is focused at the focal point F. So F is our focal point. Yes. Located in the tissue phantom. The signal is a 5-cycle tone burst with the amplitude of P initial is equal to 0.1 megapascals. Okay, so we have an amplitude of this, and the center frequency of frequency initial is equal to 1 megahertz. The center frequency is shown in figure 2. Okay, before I look at figure 2, figure 2 was probably just like graph. I wonder why they call it the center frequency and not just the frequency. Because there will be some absorption by the tissue. So is this... I'm going to assume this is the frequency of our burst amplitude. I'm going to assume this is the frequency that we're inputting and into the transducer, and that we're assuming we're getting out of it if it has a correct matching network. So 1 megahertz is what we're sending from our function generator, and we're getting 1 megahertz output. Same as yeah, okay. Actually, I'm going to assume that for now. I could be wrong. But you gotta assume. So as shown in figure 2, the signal amplitude at the source location is enough, I'm going to say that's to generate, is enough, okay, generate of higher order harmonics, but not high enough for the formation of shocks. So we're saying that the signal amplitude at the source location, so our original amplitude, I think it's this one here. That's, yeah, now that's orange. Is not hard enough for the formation of shocks. Not high enough for the formation of shocks. Okay. And therefore, no special shock capturing techniques are required in this model. I want to know what shock, I'm putting this. What shock capturing techniques do you got? How are we going to capture these shocks? I mean, what if I was having shocks? I know that one. I know that there's a. I'm actually thinking of two different things, but I know that there's a shock applied to the skin where they were using electricity on the top of it to actually get some therapeutic effects. So I was thinking about this. Maybe the skin is being focused on, but focusing on the skin's really tough because it's so close to the lens. It's really hard to focus on there. Okay, we'll see. So here's our design here. Aperture, radius of our sphere. So maybe it's a non-arbitrary line where this is drawn from. Maybe this doesn't need to be the skin. Focal point, or maybe the radius does matter. I don't know. Focal point right here. And boom, we got two materials. So that's something actually to notice. We have one material and two materials that we're penetrating. If we had, say, a fat layer, let's imagine. I don't know if they're going to do a fat layer, but in a real application, we'd have maybe a fat layer. So then we'd have three materials. And then, just draw this here. And maybe we have bone. And four materials. So maybe we also then have some reflection happening at the bone interface depending on where we're applying it to. But it looks like it's just assumed tissue. So we'll continue. The traveling time of the signal to the focal point can be computed as our time to focal point, TF, is equal to d water divided by c of water, d of tissue divided by c of tissue. Now c, speed of sound. What is d though? The traveling distance. Okay, let's look at this here. Speed of sound in our water. Okay, we can look that up. We can find the speed of sound in water. Speed of sound in the tissue. Now, not really specified, but there are... if you know what tissue you're looking at, you can actually get these. See if we knew like tissue 2, tissue 3, 4, like a bone, we can know what our speed of sound in bone is, speed of sound in maybe fat. But for this tissue, they probably have that. That's probably a value that's going to be given. Let's see. D is the traveling distance in the corresponding materials. Okay, yeah. So the time to get to the focal point is going to be the time. This is very easy. I say very easy, and we're still on the second page. Time 1 here, this is, I could say this is T1, and this is T2. Time through 1 plus time through 2 up into the focal point here. Because we're not, if we did time outwards, this could go on. Maybe it's the time until we hit our focusing point here. But if we didn't specify that, we're looking at time in tissue, we could go on forever. So time through the water, we're going to go all the way through the water. So the entire time in the water, plus the time in the second tissue, all the way up to our distance. And if we had different materials, then we would have 3 and 4, depending on what we had. And then we would just have the distance here of tissue 1 plus the distance of tissue 2 divided by the speed of sound in that tissue. So let's continue. Respectively, at the frequency of 1 megahertz, the time to focus is approximately equal to 41 over frequency. 40, no, I thought that was the units. It's 40 divided by the frequency? Here's our pulses. Here's our time. Okay. Well, let's just look at the time. It's seconds, nanoseconds here. Pulses 2 to 2. Let's keep going. Yeah, okay, so we finished our model definition. We've defined our model now. Kind of confused about why there's this division, if this is division or if this is units, because I thought this might have been units at first. We have units here. I'm going to say 40 divided by our frequency. So 40 divided by 1 mega. Wait, then that would just be... Because we already have the megahertz here. Oh, that'd be... But a megahertz is a... Okay, megahertz is 10 to the power 6. 40, so that'd be 40 here. We have 10 to the power 6. It'd be 40 nanoseconds. Is that right? Microseconds? No, I think it's nano. Okay. But we have... I'm not quite understanding that. Okay. Well, let's continue. Results and discussion. The evolution of the signal traveling from the source is illustrated in figure 3. Right here. So the evolution of the signal traveling from the source is here. So okay, I'm trying to find out where initial is, because we have, it looks like these are applied at different locations though. Under, above the line, high above the line. Okay, let's keep reading. The tone burst pulse has left the source at time is equal to 10 microseconds. The tone burst pulse has left the source at time is equal to 10 microseconds, nanoseconds. Okay, yeah, so 10 microseconds. Or, yeah, right here, 10 microseconds. Okay, leaving the source at 10 microseconds and travels towards the boundary between the water and the tissue phantom domains. Okay, so the boundary between the water and tissue phantom domains, let's actually pick this one, which it passes as t equals 20 microseconds. So does that mean that this must be our, okay, here's 20. Here's 10. Okay, let me draw on one of these. Get a smaller line. One here. One here. One here. This one doesn't even... I thought this was our tissue. Kind of getting a little bit confused by what this model is, but let's keep going. So, which it passes at time is equal to 20 microseconds, with some part being reflected back to the source. The focusing of the signal becomes visible at time is equal to 30 microseconds. Oh, this is millimeters. This is depth. Okay, let's erase these. Are these both millimeters? Millimeters. Oh, yeah, there's no time here. Okay. We only have pressure intensity here. So, okay, those... Never mind that. There's no time here. Okay, so if we were imagining... I want to draw this out then. So, the evolution of the signal traveling from the source. Okay. It has left the source at time is equal to 10 microseconds. Okay, so we have... let's draw this a little bit here. Maybe that doesn't. Maybe a graph isn't the best option. Maybe it's like this. Okay. And I'm going to say, I don't need a line for that actually. I can just draw a circle for our focus. Okay. And so it's easier to see. Let's do water here, and then they just use skin color. So skin color for the tissue. Okay. So we have our transducer, yellow. transducer is hooked up to our power supply. And the time it takes for the electric pixies to travel through this and get emitted is 10 microseconds. And then it passes the domain it passes this domain right here, water, skin, at time is equal to 20 microseconds. And some part being reflected back to the source. So we could say, I'll do a little drawing here to kind of illustrate that. Let's do green. So green is going to be our sound waves. They originate kind of from here and then here. There's more going on. I'm just going to draw it as a simple beam. Something like this. It doesn't look like this though. So it's coming in, coming in, coming in. Some's coming here, and then if I can show lighter, some's going through, lighter is going through. But then it said, we have some being reflected back. I'm using darker green for that. So we have the waves coming back this way. And this is happening very, very fast if it's only taking 10 microseconds to pass through the water. The focusing of the signal becomes visible at time is equal to 30 microseconds. So this doesn't relate to this, because if it's becoming visible at 30 microseconds, that must mean that we're taking some lag to pick up. Or maybe, does it even mean that... That's a really weird question mark. Does it really mean that our software has a lag? Or is it not high enough to be captured? Because we have it right now. We have it here at time is equal to 20 seconds. We've already got some reflecting occurring. Becomes visible to our computer at this point. Maybe that just means the time it takes to go back to our computer from our data acquisition software. And reaches its maximum. Okay, so when it says becomes visible, probably minimum pressure that we can see. As we see here, the pressure's tailing off, minimum pressure. And then reaches a maximum at 40 microseconds. I'm not going to assume anything of that. I'm just going to assume that is our maximum. But we would say maximum is here, wouldn't we? But they didn't say maximum at the focal, so we're just going to say, we're not going to say that. We're just going to say it gets to its maximum. Okay. So now we have these images here, and we see it says traveling. So ultrasound is coming in here. We have, very easy, very easy. So time here is equal to 1 microsecond, or 10 microseconds actually, 11, 10. And we see this. Oh, I'm finally understanding what this signal is. Okay. This must be our water that we're in. Okay. Okay, now we can actually do this again. Same drawing here that we did. We just recreated it. All right. I'm using orange because orange is our aperture, and I'm actually going to just draw the whole thing. This is our whole aperture. Okay. Whole aperture. Time is equal to 10 microseconds. 10 microseconds. What do we know? That it has left the source and travels towards the boundary between the water and the phantom tissue. Okay? Has left the source. And as you saw, when I saw it here, I just I simplified it and I showed one single beam as if it was non-focused almost, or yeah. And you can see here, this is the beam shape. It's actually not this shape. We're getting a shape like that. It's different. And we've left it. It looks like we're drawing close. We're drawing very close. I'm going to assume that what we're caring about is the darkest portion of this, because this actually has met the boundary. And we have this moving upwards towards the boundary. We're in water right now. Let me draw blue. You can see this is water here. This is tissue here. Okay? So we're traveling upwards. We're traveling towards the boundary. Time is equal to 20 microseconds. Okay, look at this. We have now passed the boundary. And this might not be showing up on the screen, but we have a wave here and here. These are some reflections occurring, which they said. And some parts are reflected back to the source. We have these here. These are reflections. And we've crossed the boundary, okay? We're still moving upwards. And what we're looking for is that peak intensity, that peak pressure. So next we have time is equal to 30. Now it says the signal becomes visible. And I'm looking here because I almost want to say it has been visible because we can actually see it. So I don't know what they mean by it becoming visible, but as we look at this area here on the bottom, here's our reflections. Looks like I want to call this a reflection too, but I don't want to call this a reflection. I see a weird shape going here because this side's going like this side's going like this. This could be the reflection coming back upwards off of this boundary. Superposition could be something else. Not too clear. Okay, but at time is equal to 40 seconds. Look at this, 40 microseconds. We have this. And that must be what they mean by maximum our signal reaching its maximum. Now, we want to see darker reds. Highest pressure. I don't know if this describes that well because is this the darkest red? This is looking pretty dark to me. Not the bottom, this one. So that's a little confusing. It'd be nice to have some numbers attached to these because the color scale isn't that nice. Okay. But what we do know is that, hey, we can actually describe our model. Our model has a wave leaving our source here. It takes 10 microseconds for it to leave. Another 10 microseconds to cross the boundary. And then after it crosses the boundary, 20 microseconds to reach its maximum. And that would mean that... Does that mean that it's slower in the tissue? Or does that mean that we have more distance to travel? That's making me think back to this equation here. Time is equal to this distance plus this distance. So, I don't know. It's a combination of these. It looks like we have a longer distance here. So, dt looks greater than dw dt. But, we also would need to know what is greater, seawater or sea tissue? Which speed of sound is greater? I would not guess. I would look these up. And then after I look them up, next time guess. Okay. Let's see. How many... I think a lot of it's just the images and references. Okay. So next, figure 3 also shows... Okay, we're also seeing the signal strength increase as it comes closer to the focal zone. And that's the part that's confusing. I'm not seeing this, but you know what? Let's see, actually, hold on. I just realized, maybe somebody else might have known this, but when they're saying here, okay, we know this one now. The focusing of the signal becomes visible at time is equal to 30 seconds. And that, what we're seeing here, this shape, I'm gonna erase this. This shape, we don't want to see an increase in pressure by focusing. We have good pressure. What we want to see is we want to see our area go from this shape, this much area, that much area, this much area. Focusing becomes visible we see that our focusing starts occurring here. That's why we're saying that. Okay, makes sense. And then it says reaches a maximum at time equals 40 seconds, 40 microseconds. So now we know that. I would put that green. We understand what's happening here. We understand what's happening here. We have focusing happening here. Maximum focusing. Smallest point. Let's give ourselves a pat on the back for that. Okay. So it also shows that the signal strength increases as it comes closer to the focal zone. Signal strength. And that pressure, is our pressure increasing? Because I noticed that our signal is becoming more focused. But that's the part that I was saying earlier where I was saying I don't see a difference in the colors. So the strength, how can we tell that it's increasing? I would like to see the numbers. Maybe I'm wrong about that. Let's go. This is confirmed by the plots. Oh, in figure 4. By the plot of the signal at the water tissue interface and at the focal point depicted in figure 4. Okay. So we got ahead of ourselves. Let's take a sneak peek. Let's find these figures. Figure 5. Here we go. What do we have on here? What are the units? So we have time. Relative pressure probes. Must be pressure. Don't know the units, but see here? Look at that pressure. Why is it blue? Tissue. Oh, they're just saying that. They're saying this is the tissue? Z of tissue. Z must be the tissue interface. Is there another one? No. I'm assuming we're at the tissue interface here, tissue interface here, tissue interface here. Tissue interface is getting less pressure, but then our focal point has very high pressure. So this is focusing, non-focused. Focusing, non-focused. So if we would see this being higher. The acoustic pressure amplitude at the focal point is about 10 times greater than that of the water tissue interface. Okay, hear this? Yeah, I can see that. We're at about, yeah, maybe like 3 or something here, 5, I don't know, less than 5, 4. We're at like 90 here, greater than 10 times. So it's about 10 times greater. Okay. Another observation is that the position pressure peaks are almost twice as high as the negative ones. Oh, you know, I actually wasn't looking at that. That is very good. Right here. So positive pressure peaks are greater than negative. Positive pressure, that's going to be compression. Rarefaction, I believe. We have our graphs here, pressure, and this is like if our pressure is going like up, it's like half down, up, and then like a little bit like that, back up. This point here is, these are rarefaction points. These are the points when we're having compression, and this is expansion. Within the high, I'll just say it as this, you know, we're having pressure. Pressure is acting upon our tissue and will be pressurizing it. It'll be compressing things. And we're going to have expansion down here with our negatives, with our negative points. The acoustic pressure amplitude at the focal point is about 10 times greater than that of the water tissue interface. Another observation is that the pressure peaks are almost twice as high as the negative ones at the focal point. This indicates that the signal becomes highly nonlinear as it reaches the focal zone. Oh, highly nonlinear as it reaches the focal zone. Let's see here. Yeah, these are, I see. Nonlinear, let's make an assumption here, means that when we have these, oh, that's not good. Linear, nonlinear. Could also be this here. Actually, no. I'm gonna say this. I'm sticking with this. Okay. Highly nonlinear as it reaches the focal zone. Okay. Figure 5 shows the frequency content of the recorded signals. The frequency content of the signal entering the tissue phantom is not much different from the source signal. That is, the propagation up to this point is linear. Okay, let's read this again. The frequency content of the signal entering the tissue phantom, frequency content, okay, it's not much different from the source signal. That is, the propagation up to this point is linear. Okay, I can give this a green. Yes, it is linear. Very linear right here. You're seeing this. The frequency content of the signal isn't different. Okay, frequency content. Probably, if this is our footprint, this is our footprint. Linear footprint. Linear frequency content. Nonlinear. The signal at the focal point is, however, highly nonlinear. We have answered that, which is seen from the number of generated higher order harmonics. The plot of the minimum and maximum on-axis pressure calculated are depicted in Figure 6. So actually, let's see. Figure 5. Oh, okay. Let's go to Figure 5. And we can see these highly nonlinear by the number of generated higher order harmonics. Let's go there. Figure 5. Okay, so blue's tissue. Here we go. Okay, we have one here focused around this point here, high at 1, 2, 3, and these are our harmonics. Fourier coefficient. Okay, these are our harmonics because it's going 1, 2, 3, 4, bump, 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 and this should keep going like this until it decays out. But if you know about a Fourier coefficient, these are substantial. This means a pattern. This is one pattern, but this pattern is just around 1. Okay. So now we've answered that. Okay. Number of generated higher order dynamics, we have seen those. The plot of the minimum and maximum on-axis pressure calculated are depicted in Figure 6. The values are computed according to these formulas. Okay, let's look at the formulas. And I'm going to go straight to what the units are. And are normalized with respect to the maximum pressure at the focal points. So minimum and maximum on-axis pressures. Okay. Well, let's change this to pink. Okay. Pink here. Minimum on-axis pressure equal to the minimum this. Maximum. Okay, we've got this. Maximum this. Rest, not feeling too certain about it, but it says here, let's look at Figure 6. Okay. P maximum. Oh, this must be, I think I'm getting this now. Okay. Is it this guy? Or is it with our Fourier? No, it's this guy. So, for positives and negatives. I think that said, where was it here? Minimums and maximums. So, minimums, maximums. Okay? On axis pressure. So, I think this is over time from 0 to the end of time. Pressures. And if we go to 6, maximum. Okay, yeah, maximum here. And negative maximums. But they're divided by the maximum. So we're actually here not getting the actual pressures, but we are getting a percentage. Not really a percentage, because this would have to be 100%. It's a ratio. We're getting a ratio. 90%. You know, I like thinking about percents more than ratios. So 100%. 100%, this. And this one. Okay? And these guys. Smaller. Smaller relative to the maximum. So this, we were saying that actually, like, let's test this here. We were saying that the maximum of this guy is about half of this guy. Let's see. 0.5. So our maximum of our lowest point, approximately half of our highest one, which we saw about here. So we can confirm that. I'd like to say, does it hold true for... I went down too far. Does it hold true for these? And, you know, these are their ratios of this. Can't tell. Okay. And or normalized with respect to the maximum pressure at the focal point. Okay, well now we know what that is. Now we know what Pmax was. So figure 6 shows that, oh, here we go, what we just saw. The pressure, I want to say this. The maximum on-axis pressure is almost twice that as the minimum on-axis pressure, which is a distinctive feature of nonlinear propagation on a HIFU signal. The bounds of the focal zone are also seen in figure 6. Let's look at the bounds. Boundings here. Okay. Z divided by F. Distance. Z distance divided by focal. No, frequency. Frequency, right? Distance divided by frequency. 0.4. 1.6. And at 1. Must be distance away from our focal point. Correct? Incorrect. Let's see here. Do we have distance on this graph here? We have time. We have distance here. No, we have frequency. Is it related to frequency? Well, some way that says as we move some ways away from our focal point. Could be in time. Could be in distance. But this is our peak. I'm thinking if this was distance, this would have to be our boundary, but these lobes look very similar, that these may just be side lobes. Okay, let's get past that and continue that. Okay, so now we've actually finished looking at our problem. And now we can get onto the Comsol implementation. That's going to be exciting. So I'm actually going to pause this here, even though we didn't get to it. But we've identified our problem, and we've also seen our results. So next time, we're going to look at our Comsol implementation. All right. Thank you.